Namaskaram. Now, in the last class, we were introduced to the basics of our Cartesian coordinate system, and in that we have the x-axis, which in our experiment represents the passing of time in seconds, and the y-axis, which represents different distances in meters. This system was used to get a picture of any equation that we have, just to make our calculations and stuff a little bit easier. Now we're going to see how we're going to do that in individual steps. And we got introduced to the idea of a scale, a way of showing the different quantities in my Cartesian coordinate system or my Cartesian plane. And I've just made a small change to the diagram compared to the previous lesson. We know that when we say scale, for example, earlier we said 1 centimeter equal to 1 second, 1 centimeter equal to 5 meter. We know what that means now, but just to prevent any confusion, where you look at it and say, wait, 1 centimeter, how is it equal to 1 second? Or how is 1 centimeter equal to 5 meters? We know that it's not equal to. I'm just showing 1 centimeter on this line to represent 1 second, and I'm showing 1 centimeter along this line to represent 5 meter distance, right? Just a way of showing what we refer to as a legend or a scale. We know that, but just to prevent that equal to sign from causing any confusion, I've replaced the equal to sign with like an arrow, right? So this basically is a very clearer way of showing that, okay, in this diagram, 1 centimeter along the x-axis on this diagram shows a time of 1 second, and 1 centimeter along the y-axis in this diagram shows the distance covered by the car of 5 meter. So just a small minor change I made to that. Now, our experiment primary story pretty much remains the same. Just giving you a quick recap. If you want the details of the experiment and where this equation came from, check the previous lessons and you'll get the entire picture. A quick summary: we have our car going on a straight road. As it travels, time passes, distance is finished, and we want to get an idea of the relationship between how much distance it has traveled after a certain amount of time. And when we investigated that, because the car was going at a steady speed of 5 meters per second, the relationship that told this entire story was y equal to 5x, which we refer to as an equation. And where we left off was, we now want to find a way of showing the same equation, and therefore of showing this experiment, because this equation is basically the story of this experiment. So we now want to find a way of showing the same equation, and therefore of showing this experiment as a picture, in a more kind of a visual way. We want a picture of this equation so that our calculations can become a little bit easier. That is our objective right now throughout the course of this lesson. So how do we go about doing that? What we're going to do is we're going to take a few specific stages in this experiment. Not every single point, a few specific points in the journey of this car. Right? And for each of those points, there's obviously a particular value of time elapsed. That means a particular value of x. And for that amount of time, the car has traveled a particular distance from the start. So there's a fixed value of y. So we will take for these points, in this case I've chosen 6 points. For those 6 points, we get the value of x, and then we get the value of y. Using that, we take those 6 points only, those 6 stages only, and draw them on our Cartesian plane. This process of taking points from the experiment and drawing them or showing them on the Cartesian plane, we refer to this process as plotting. The process of plotting the points, plotting the stages. We put them on the Cartesian plane, and then we'll slowly start to see if there's any distinct shape that starts to appear on our plane. So let's go ahead and do that. Where do we start from? Let's start from the beginning, right? So the car is obviously right here, right at the start, and at the start, no time has elapsed and no distance has been traveled, because everything is measured from here, right? This is what we saw earlier as initial conditions. What are the conditions at the start of the experiment? X is 0 seconds, y is 0 meter. Now, you can also get that from the equation, because this equation, y equal to 5x, covers every single stage in this experiment. Any stage in the experiment, if you want to find out y, the distance traveled for a given amount of time x, multiply x by 5, you will get y, because this is basically distance is equal to speed into time. So you can get the initial conditions also from this equation. Plug in x is equal to 0 seconds. When you plug x equal to 0 seconds, 5 into 0, y will also be 0. That process we do and we show it on this table. In the table, first column x, that is the amount of time that has elapsed from the start in seconds. The second column, for that amount of time, for that amount of x, how much distance the car has traveled, y in meter. That is my second column. And then to put this stuff on the Cartesian plane, we need to know the x first. We hold the x and then we change the y and then we get the point. We get every single point in this experiment in our plane. So for that, we need what we call as ordered pairs. The ordered pair is just the point, which basically has the x first, the x coordinate, and the y information second, or the y coordinate. So when I say 0, 0, I'm basically talking about this, which is basically this stage in the experiment, 0 seconds, 0 meter. So this is the ordered pair. This point is what will be plotted on the Cartesian plane. So now we finish this. Now we got the ordered pair. Where will this particular ordered pair be on our Cartesian plane? It's 0, 0. Initial conditions. Obviously, it is at the start of my Cartesian coordinate system, that is 0, 0 here. Why is it here? Because this is the x-axis measuring time and we are at the 0 second mark of the x-axis right at the beginning. And from here itself, the y-axis also starts, right? Measuring the distance. And for the y-axis also, we are at the start. We are at the 0 meter. So we get 0, 0. That is why this point is the point from which everything starts. We know this point is now the origin. So basically, the origin on our Cartesian plane is nothing but the initial conditions point. 0, 0 is here. Now in the same way, we start from the experiment, equation, get the point and then put it on our Cartesian plane. It's one story. It's just one story. Let's do that now. After 1 second, a time of 1 second has elapsed. The car is going, right? Steady speed. After 1 second, how much distance has the car traveled from the start? We can use our equation and get it. Put x equal to 1 second. Y will be what? 5 meter per second into only 1 second. You will get the distance traveled is 5 meters. So when x is 1, y is 5. We show that as the second entry in our table. X is 1, y is 5, and therefore the address or the coordinates of that point, the ordered pair becomes 1 second, 5 meters. This is the next point that we have to plot on our Cartesian plane. And now remember why we had the Cartesian plane, right? We keep the x-axis and y-axis perpendicular, because if I now want to plot a point like this, the fact that they are perpendicular makes it wonderful, because now all I have to do is first change the time by holding the distance, then hold the time and change the distance, and then I can get the point, which is a combination of both changing time and changing distance. We saw that in detail in the last class. Let's do that right now. We'll start from where we were. We were at the origin. Now what we do, we need to go from 0, 0 to 1, 5. So the first thing that we'll do is we'll decide to move along the x-axis, that is along the time axis. So we move along the time axis, and when we move along the time axis, we lock the distance. We don't move up and down. So we will keep the distance obviously locked at 0 meter, because that's what happens when you move along the time axis. Distance doesn't change because they are perpendicular, right? And we'll only change the time. So we'll now do that. I've shown it by this arrow here, right? So you start from 0, 0, keep the distance locked at 0 meter and start moving. You can just imagine you're taking a walk. Take a walk and now you go to this point, which is 1 second. Now on the plane, this point is actually 1, 0, time of 1 second and distance of 0 meter. Now this is not an actual stage in our experiment, because there is no stage in this experiment where 1 second has elapsed and the car is still at the start. It's still at the 0 meter mark. It is not. But we are getting there. We are halfway there. At least we now got the time of 1 second. Over here, the distance is also 0 meter. Now what we do, we don't want to change the time. So we'll keep the time locked at 1 second. Now we will move along the y-axis. I'm actually moving parallel to the y-axis because I've shifted along the x-axis, but the direction is the same, right? So I can measure my movements just by looking at the y-axis. I've just I'm moving along that direction, but just a little bit shifted. I'm moving parallel, right? Now, keeping the time locked at 1, I need to move 5 meter. I need to move to the 5 meter mark along the distance axis, along the y-axis. So we'll do that and go here. That is what I have shown by the arrow, the small arrow here. And to show that I'm moving in this grid-like 90-degree fashion, I have shown the 90-degree, the angle symbol over here between the first movement, the first arrow, and the second movement, the second arrow. So first movement, keep y fixed and move along x. Second movement, keep x fixed and move along y. Then the combination of the two will achieve the final point in the experiment that you need. And that is marked by this cross here. So this cross that you see is this particular point, 1, 5. Just like the first cross that you saw was 0, 0. That is here, and that matches this stage in the experiment. Just for clarity, I have also shown that 1, 5 point on the experiment diagram as well. So you can always make the connection between this, the equation, the ordered pairs that come from the equation, and the points that I'm plotting which come from this table. So again, I reiterate, it's all just one. Different versions of showing the same story, right? Now we are here. Then what happens? Then one more second elapses, and we know that with every passing second the car travels another 5 meter because the speed is 5 meter per second. The next piece of information, the next stage is 2 seconds have elapsed from the start, right? A total of 2 seconds have elapsed from the start. Where is the car now? Well, you can again get it from the equation. Put x equal to 2. 2 seconds from the start. X equal to 2. Y is 5 into 2, 10 meter. That means after 2 seconds, the total distance that the car has traveled from the start, remember everything is measured from the start, right, is now 10 meter. Now we show that here, which is now our third point. X is 2, y is 2, 5s are 10. The point is 2, 10. Now, we can get to 2, 10 starting from the origin again, right? So I can go from here, hold it, go to 2, hold it at 2, and then move up to 5 times 2, move up to 10, right? And I can get it there. Another way of doing that, instead of going all the way back from the origin, you can go from where the car is at the 1 second mark, from where the previous point was, right? And then you don't have to go all the way from here. You just have to go from here to here, which means I'm starting from here on the Cartesian plane. That's another way of doing it. You can do the whole thing in one step from the beginning, or you can do it in 2 steps. Go from 0, 0 to 1, 5. Go here, and then from 1, 5 we can go to 2, 10. Let's see how we can do that. Imagine you're standing at 1, 5. That is, you're in this position in the actual experiment. That is here in the Cartesian plane. 1, 5. Now from 1, 5 we have to come here, which is 2, 10, right? We'll do the same thing. We will now lock the distance at the 5 meter mark. Lock the distance at 5 and change the time by how much are we changing the time? We are going from the 1 second mark to the 2 second mark. So we are going from 1 to 2, but the change in time is only 1 second, right? 1 second elapses from second number 1 to the 2 seconds, to the 2 second mark, right? So 1 to 2. The change is 1 to 2, so only 1 second is a change. So we go from here to here, but we are going here because we are starting from the point 1, 5. So we are actually going along the x-axis, but because we start from here, we are a little bit shifted, right? We are going parallel, same direction, same thing along the x-axis, but not on the x-axis, just shifted up parallel. But this distance is the same as this, right? It's just in a different position, that's all. So we'll hold the distance at 5 meter and change the time by 1. So from the 1 second mark, we'll go to the 2 second mark. Then we'll go to this point here. This point here is not an actual stage in our experiment. Because what is this point? This point is 2 seconds but 5 meter. 2, 5. 2, 5 is not a stage in our experiment. Because in our experiment, after 2 seconds, the car is not at the 5 meter mark. The car is at the 10 meter mark. But as always, we are halfway there. Come to 2, 5. Now at least you have reached the second number 2. right? You reach the 2-second mark, lock the time, lock the x-axis and move along the y-axis, change in this direction or the distance axis. Again, you are moving parallel to the y-axis, same as the y-axis but little shifted. So you can look at the y-axis and see how much you are moving. Now you will move from 2,5 to 2,10. So your change is just 5 meter. It's not 10. You are reaching the 10 meter mark, but you started from the 5 meter mark. So your change is only from 5, 6, 7, 8, 9, 10. You've changed by 5, and then I've shown that by this arrow. And then you've reached here. So you can reach this point in two ways, from the start or from the immediate previous point. It's up to you. In both cases, you're still doing that grid-like motion. These are just two ways of doing the same thing. Then you reach 2,10, right? The rest of it is the same. I have shown the arrows, as you can see. I've shown the arrows, and you can continue doing that. Basic processes, find out what time you're looking for. So 3, 4, 5 seconds from the start. How do you get the distance? This equation tells the story of every point in this experiment, every single value of x and y, right? Plug in x, 5 into that will give you y. Enter that point here, enter the details here. Third entry, this is the 3,15 entry, 4,20, 5,25, you get the ordered pairs. And then once you get the ordered pairs, you do the process of plotting, that is drawing the ordered pairs as points on the Cartesian plane using our grid-like movement for simplicity, and we get the points. So if you can do that on your own as well. You can draw a picture like this, preferably neater than mine, and finally get the picture. Now that we have finished that, we just take a look. We've not yet got everything, right? Because if you see what is on my Cartesian plane, I have only 6 points, right? I have only 6 points which match these 6 entries, which come from these 6 stages in the experiment, right? So I have only 6 values of x and 6 values of y. I don't have all the values of x and all the values of y. I don't have every single stage in this experiment yet. That's what I want. I want the full experiment given by this equation to be fully shown on my Cartesian plane. But I have only 6 stages. I have only 6 points, which is fine. As always, we are getting there. Now, even before we complete the picture, get the picture that we want of this equation and therefore this experiment, we are getting there. But just before that, just take a look at what we have and just sort of get a mental picture of where these 6 stages or where these 6 points lie, and just sort of somewhere in the corner of your mind, start making up your mind as to what shape seems to be forming on our Cartesian plane. We're not going to jump the gun yet, right? Every step we're going to see why we do it. But just take a step back and see what is the shape that now seems to be slowly forming on our Cartesian plane, which seems to be what the picture of this equation is slowly going to start looking like. Now, while you're looking at the shape that these points seem to be taking, we'll get there very soon. I just want to stress on something which technically need not be stressed on right now because it's very obvious, it's very clear, but I'm going to stress on it because it's of great value later on in this lesson. And that is, I want to take your attention to these 6 points, and I want you to think, based on how these 6 points have come, what do these 6 points on this picture, on this Cartesian plane, what is it that they have in common? What do these 6 points have in common, right? Now think about how these 6 points came. These 6 points came from this experiment, right? What did we do? We took 6 different amounts of x, 6 different time values, plugged in those time values into this equation, distance equal to speed into time, got the distance traveled for those time intervals by the car, showed them as points, and then took each of those points, did our grid-like movement and put them on this plane. That's basically the story, right? Because we did it like that, these 6 points essentially have come from this equation, right? The equation gave us the points and those points were plotted, right? Because of that, one way of looking at it is, What do these 6 points have in common? These 6 points have one very simple thing in common. In order to locate each of these 6 points on the Cartesian plane, what did I have to do? The amount I moved along the x-axis, right? That is along the time axis. The amount I moved along the x-axis, whatever that amount was, that amount had to be multiplied by 5, and that is the amount that you had to move along the y-axis to locate the point. For each of these 6 points, that was true. And we can see that with a couple of examples. For the first point, you moved 1 along the x, and you moved 1 into 5 along the y. For the second point, you moved, second point after the origin, right? You moved 2 along the x, and how much did you move along the y? 2 times 5, 10 along the y. 3 into 5, 15. 4 into 5, 20. 5 into 5, 25, right? Now, you might be thinking, bro, that's obvious, right? Yes, it is obvious. And why is it obvious? Because all of this came from this equation, from this table, right? And what does this equation tell you? For any value of x, the distance is 5 times x, right? It's 5 times the time, because 5 is the speed. So, since you use this equation, isn't this obvious? It is obvious. It is 100% obvious. A fancier way of saying that is, see, for any point on the Cartesian plane, we just gave some fancy words, remember? For any point on the Cartesian plane, the amount you move along the x-axis was called the x-coordinate of that point, and the amount you move along the y-axis was called the y-coordinate of that point, right? So, saying the same thing using our coordinate lingo, we basically say that one thing that all these 6 points have in common is for each of these 6 points, the y-coordinate of these points is equal to 5 into the x-coordinate, or 5 times the x-coordinate. That connects all of these points, which we know is obviously the case. So, y-coordinate for each point is equal to 5 into x-coordinate. Basically, that means y is equal to 5x. And since y-coordinate represents distance traveled by the car in meters, and since the x-coordinate represents the time elapsed in seconds, and 5 is obviously the speed, this y-coordinate equal to 5 times x-coordinate is just a very fancy way of saying the same thing. Distance in meter traveled by the car is equal to its speed into the time in seconds. Distance is equal to speed into time. It's just a fancy way of saying this. So, y equal to 5x now becomes y-coordinate is equal to 5 times the x-coordinate. So, now we are ready to start seeing what shape this entire diagram is taking, and therefore what shape this equation is going to have on our Cartesian plane. Now, if you've done some math in high school and college, etc., you've probably done a process like this, right? You had some experiment, you had an equation, you used the equation, you got a few points, and you plotted them on this plane. And then what is the next step that you do, right? Now it's almost a habit, because you've probably done this many times, right? You see these points here, and you're like, hey, wait a minute, these points seem to be nicely fitting into a nice smooth straight line. And without even thinking too much, you just take your pencil and ta-da, you just draw the line, right? I know there's a temptation to do that, but one suggestion here is, whether it's math, whether it's science or life, I mean, they're all the same, really. We shouldn't do things just because it's like a habit, right? It's almost like a nervous twitch. It's like you see the points and you draw the line, right? Any step that you do, there must be some reason, there must be some motivation or incentive, some purpose that that particular step has to serve. Simply doing something may not be the best way to go about things. So we will now resist that temptation to just draw the line that seems to be the case, seems to be the pattern, right? We will resist it, and we'll take a moment and see what purpose will that step serve, right? Let's take a moment to do that. Now, why are we doing all this? Let's keep reminding ourselves, why are we doing all this? Why did we plot these 6 points? These 6 points obey this equation. And therefore, they are showing you these 6 stages in the actual experiment. There's all different ways of saying the same thing, telling the story of this experiment. So these 6 points do that fantastically. But there's a problem. These 6 points only show you these 6 stages. But are they the only stages in the experiment? Absolutely not. Time is continuously passing and the car is continuously traveling different distances from the start, right? So how many different stages are actually there in this experiment? There are infinite points, infinite stages, right? Just between the first and the second stage that we chose, 0, 0 to 1, 5, there are infinite values of x, right? Infinite values of time elapsed between the 0 second to the first second. For each of those values of x, for each of those time elapsed, the car is at a new position because the car is continuously moving, right? So for each of them, technically, if I want to find out where the car is, for each of those x values, you plug them into the equation, y equal to 5x, you will get unique distance values. That is true just between these 2 points. It's also true between these two, these two, these two, these two, and beyond. Saying the same thing over here. Between these 2 points, there are infinite values of distance and time, right? Between these 2 points, these two, these two, these two. There are all those points in between. I don't know where they are on this picture, but wherever they are, they will match the different stages in the experiment, right? If this picture has to be of use to me, it should give me a picture of the entire experiment, of this full equation for all the points, right? Then that picture is useful to me. Right now it shows me only 6 stages. Now we are coming to the topic of incentive, motivation. We now want this picture to not just have these 6 stages in our experiment. This picture must have all the stages in the experiment, all the different values of x, and for all those different values of x, it must show me what the distance is, what the y value is, and not just for this interval, not just from here to here, even much later, after the 5 second, 25 meter mark, much later also in the experiment, it should have all that information in this diagram, where the car is, how much distance the car has traveled after a certain amount of time. Any time in this experiment, all that information should be there, not just 6 stages, right? That is what we want. Then this diagram becomes useful because then the whole story is shown here very clearly. Now, how do we do that? Well, if you want to do it in the way that you did the 6 points, that is a fool's errand, because then you will lose the will to live. What do I mean by that? If we try to do it like how we did it for the 6 points, what do? We'll have to take every single value of x or time elapsed, say from here to here. For each of those values of x, plug them into this equation, y equal to 5x, get the value of distance. Put those x and y values in this table. So all the points in this region between 0, 0 and 1, 5 will be now entries in this table between this entry and this entry. Then all the points over here will come as entries between this entry and this entry. Then between this point and this point will come here. And how many points you'll have? Infinite points, right? Billions and billions and billions of points. And you do that, then you get all these points on the table. Then just like you did for these entries, you will take each point, start with your origin, then do your grid-like movement x and y and x and y, and then all the points between these two will come somewhere here between these two. All the points between these two will come somewhere here between these two. You plot, go like this, go like this, go like this, go like this, plot, and then you will be able to show all the stages. Think about it. If you're going to do that, I mean, you might as well just give up, because that's just going to defeat all the advantages that this process could have, because just doing the process itself, your whole life will go and you still won't finish, right? So that is not the way. We want the picture. We want all the stages, but plotting every single stage physically is definitely not the way. Then, if that's not the way, what is the way? So what is the solution to this problem that we have? Well, why don't we start with the 6 points that we actually chose and plotted, the 6 stages that we do have. It's a good idea to start with what you know, start with what you have, and then see where we go, right? So let's look at these 6 points, and we know that we've plotted them on our Cartesian plane, and let's look at how they all line up, right? This is where I want you to think of a childhood story. And everything I'm about to tell you right now is that story, and that is Hansel and Gretel, right? Now, if you remember Hansel and Gretel, what was the gist of the story? The gist of the story was, if you place enough number of breadcrumbs at different locations, they can be reasonably spaced. They don't have to be one after the other touching each other, right? You place one here, you place one there, you place one there, you place one there. If you place enough number of breadcrumbs from where you are to where you need to be, and then you just take a step back, you take a bird's eye view and you look, you can clearly see the shape of the path that those breadcrumbs are forming. You don't need a breadcrumb at every single point. You can fill in the details quite easily if you just take a step back and see what shape they are making. You can clearly see, are these breadcrumbs making like an S? Are they making like a Z? Or are they making like a straight line? Right? So if you have enough number of breadcrumbs, you can use those breadcrumbs as clues or like milestones, or you can use them as hints and basically take the hint and see what shape that is forming. Once you see the shape, then you can't unsee the shape. Then you can just draw that shape and then you're settled. You're home free. We are going to basically be doing Hansel and Gretel here. And we know why we want the shape right now, because we want all the other stages. Now if you look at these 6 points, don't think of them as plotted points from the experiment. Just think of these 6 points as breadcrumbs. So you have 6 crosses here, 6 breadcrumbs. And imagine you're Hansel or Gretel or whoever else, right? And you're looking at it and be like, hey, wait a minute. This is very clear. If I have to start from this point, aka this breadcrumb, and if I keep moving in the same direction, that means I don't change my direction, I don't change my angle, I just keep moving at the same angle in the same direction from this point, you will automatically hit all of the other points that you have plotted and beyond. Which means the path that these breadcrumbs are screaming out at you, are yelling out at you, is they all are part of the same straight line. So you can use these 6 points as clues and take the hint that now you can be completely confident that if I complete the path and complete the picture, that is, if I join these points with a smooth straight line, that is the path of this experiment. That means I can completely be sure that all the points on that straight line will represent or will show each of the stages, each of the infinite stages, each of the infinite sets of x and y values in the actual experiment. I can completely be sure that all those stages will be there on this line. Just like my 6 breadcrumbs, all the ones in between will also be on this same straight line. And then we have incentive to therefore draw that line and complete the picture. Another way of saying the same thing is, once I draw this line, I can rest assured that had I done that laborious process of taking every single x value, multiplying by 5, getting the y value, putting them on this table and then plotting them one by one, had I done that, I don't have to do that, but had I done that, I can be completely sure that all those points that I end up plotting, if I do it one by one, they will be on this line that I draw. They will definitely be on this line that I draw, and therefore I don't have to do them individually. I don't have to plot them individually. Those points will be on this line. So when I draw the line, the points between these two will be between these two on that line. The stages between these 2 points will be between these 2 points on that line, and so on and so forth, right? You can think about it from here. If you had put them in this table, the entries between this entry and this entry, if you had done point by point using the equation, all those entries, when you plotted them, they will be between these 2 points on that line, not anywhere, on that line, and so on and so forth, right? So Hansel and Gretel saves the day. Now we have incentive to draw the line through these points and therefore get the final picture of this equation, and therefore the final picture of every stage in our original experiment. So now, thanks to our friends Hansel and Gretel, we have drawn the line and connected all the 6 plotted points, and we've also extended it and got the picture of our equation. Now, before we go ahead, I must apologize for how absolutely untidy this diagram looks. This itself I struggled and took about half an hour to draw. So this is also a plea to all you lovely people. If you have some suggestions or tips of how to make my board art better, I'm all ears. And actually, better than that, if you have some free time, you please come and help me do this stuff. I'll be even more grateful. Anyway, so I hope you can get the basic idea here, even though this is such a horrible diagram. I'm sorry for that. But at least now, thanks to Hansel and Gretel, we have got our picture. We've got the picture that we wanted for this equation and for this experiment. And now we know why this line is so important, right? Because we took the hints that the 6 points gave us and we drew the line and we realized the significance of this line. That's why I allowed you to draw the line, because now we know the significance of this line. What are the significance of this line? The significance of this line is that now we can be dead sure, we can rest completely assured that every single point on this line matches every single stage in the actual experiment. That is, in the actual experiment, all the different values of x and y, of time elapsed and distance traveled that come from this equation, each of those various stages, each of those infinite stages, those points will be exactly on this line, and they will be nowhere else on this Cartesian plane. They will only be on this line. We can be completely sure that that's the case. Another way of saying the same thing is, I can take now, we can do the whole journey again and see what that means. I can take any random stage in this experiment. I'm not taking the 6 plotted points. I'm taking any random stage. I've shown that in this diagram here. I've taken a time interval of x seconds. X seconds means I don't know what it is. X could be anything, whatever you choose, right? X seconds from the start. In this particular stage, I have put x at some value of time after the 4th second and before the 5th second. It need not be in between. It could be absolutely any point. It need not even be here. It can be anywhere else along this road. Okay, I've just taken a random instant of time, x seconds after the start, and after that, when that time elapses, x seconds after the start, the car has traveled some distance. Again, that's unknown to me. Some distance y from the start, right? So I have this stage x comma y. Now, if I want to find out what the value of y is, that is what the distance traveled for that x amount of time elapsed, I obviously use this equation. So just like I did for these points, I'll plug in that x into this equation, y equal to 5x, and I'll get the value of y that the car has traveled, the distance the car has traveled after this time x, right? And that value of y will be 5x. This could be applied to any random point. I've just taken a completely random stage. Once I do that, what do? I can then put that in my table, just like I did for the 6 points. Same thing. I can put it in my table, x amount of time, y amount of distance, and I can get an ordered pair, right? X comma y, where I know that y is 5x, just like all the previous points, nothing different. Now, the beauty of this line is this, and we're coming to it. If I take this x comma y, and if I now go and plot it on my picture, what do? Same thing as I did before. Start at the origin, don't change the distance, don't move along the y, move x units along the x axis, small x units along the capital X axis, right? Move x units here, I'll reach here, right? Hold the time there, lock it there, right? I need to locate the point x comma y. So I've gone till the x mark here. I'll hold the time at x. Now I will move along the y direction, right? Along the y axis. And how much do I move? I move y units or y meters, right? Along the y axis, where y is 5x, right? Obeying the equation. Now, what this line tells you is that if you do that, and if you now start from this x mark and move y units up, that is, you move 5x units up, right? You can completely be sure that that final point that you locate, it will be on the line that you have drawn. No questions asked. You can be dead sure that point that you locate, which I have shown here as the point x comma y. X coordinate is x and the y coordinate is y, because it's a random point. I don't know the value, so I'll just say x and y. But you can be sure that since you've drawn the line using Hansel and Gretel's understanding, you can be completely sure that that stage, when you actually plot it, it will completely be on this line. It will not be anywhere else, which is further proof that every stage of this experiment, when you actually plot it, it will be on the line, which means it's great. You don't have to sit and plot every single point. You use your 6 points, you see the shape, you draw the line. You don't have to plot every single point. Those points will be on this line. Those stages, those different values of x and y, x and y, x and y, they will be on this line. The same thing if I want to say it in reverse. What that essentially means is I can take any point on this line, any random point on this line, like for example this. If this point is on the line, that means I know for a fact that that point's y coordinate, that is this distance, will be 5 times that point's x coordinate, no doubt. I'm just saying the same thing in reverse. Right? Just saying the same thing in reverse, that now every point on this line, you can be completely sure that the point's y coordinate will be 5 times the point's x coordinate. And this is something I alluded to earlier in the lesson, and there also you probably wanted to kill me, right? I kept on banging on one point, which is before we drew the line, when we just had the 6 points, I said, let's pay attention to what is common to those 6 points. And we realized that since those 6 original points that I plotted came from this equation, that is these 6 points, we realized that what was common for those 6 points was that for each of them, the y coordinate was 5 times the x coordinate. Now the significance of belting that point to the ground comes through, because what we realize is that logic can now be extended not just to those 6 points. It can be extended to any point on this line. Any point on this line. If the point is on the line, if that point is on this line, you can rest assured that for that point, the y coordinate of that point will be, without a shadow of a doubt, 5 times the x coordinate of that point. There is no doubt about it, which means all the points on this line fit this relationship. Y coordinate is equal to 5 times x coordinate, not just the original 6 points that we plotted. We now are able to extend it thanks to all the understanding that we have now, thanks to Hansel and Gretel, basically. So now that we've got the picture of our equation y equal to 5x, y equal to 5x on the Cartesian plane looks like this. It's a straight line like this through the origin. The question now remains, okay, we did all this stuff, oh my god, I'm fried. Yes, we are. But what is the purpose? What is the utility of this? Now, if you think back to the utility of equations themselves, one of the things we said was, yes, it's a mathematical model, and now this is a picture of that mathematical model. But one of the things that we said about the utility of equations is they help us make predictions for any situation in the experiment, right? So for example, let's take that here. The utility of this equation is, supposing I now have a question. I want to find out where the car is. That is, how much distance the car has traveled from the start after a time of 1.5 seconds from the start. That means x has now reached the value 1.5 seconds from the start, right? Somewhere between 1 and 2, right? At that particular instant in time, where is the car? What is the y value, right? This is where equations become very useful. If I know that the relationship between x and y is y equal to 5x, I can make that calculation using what we refer to as algebra, right? Putting in the values in an equation, solving the equation. This is the field of mathematics called algebra. Perfectly fine. We did this in the earlier lesson as well. X is equal to 1.5 seconds. Y is related to x by the equation y equal to 5x. So substitute x as 1.5. Y is equal to, I'm just adding the units so that everything is clear, 5 meter per second, speed of the car, into 1.5 seconds. The second and second will cancel. I'll get more into units later on. The answer will be 5 into 1.5. I think 5 into 1.5 is 7.5 meter. My mental math is horrible. Y is equal to 7.5 meter. Perfectly fine. We've got it from the equation, right? Now the utility of this picture of the equation really comes to the fore, because it gives us an alternative way of getting the same answer without having to do all this kind of substitution. And as we'll see later on in the course, there are times when we have an equation which is a bit too complicated and it just takes a lot of time to do the substitution and get the answer. In those cases, if we can get a picture of the equation, we can then use that picture and get the same answer without doing any kind of complex computation. That's what we're going to see over here. Let's come over here. We have the same requirement. We want to find out what is the y value when the x value is 1.5 seconds. So what do? We start at the origin, right? We'll keep the distance locked at 0 because right now we don't even know what the distance is, right? We want to know what the distance is after 1.5 seconds. So we only know the time. So let's start with what we know. We'll keep the distance locked at 0 and we move along the x-axis in the x direction to the 1.5 second mark. Now we are here, right? Now we need to know what is the distance the car has traveled at this 1.5 second mark. So we've come from here to the 1.5 second mark here. Okay. Now we are here. Now we'll lock the time at 1.5 seconds and start moving up. As we start moving up, we are getting different values of y for the same value of x, 1.5. Where do we stop? We don't know where to stop because we want to find out the distance, right? This is where the line comes in. We will draw a straight line up and hit this line. That's the dotted line I've shown here. Drawing it straight up along the y-axis or parallel to the y-axis, and I will hit this line. When I hit this line, I stop. Why do I stop there? Because I know now this point that I have hit, what is special about this point? This point is on this line. And what is special about that? Thanks to Hansel and Gretel, we know that if this point is on the line, we can rest assured that the point's y coordinate, which is this much, which I can pull it parallelly and measure it on the y-axis here. The point's y coordinate, since this point is on the line, for every point on the line, the y coordinate is 5 times the x coordinate because every point on the line fits this equation, right? Therefore, once I extend and I reach this line, I know that this point's y coordinate will be 5 times its x coordinate. It will be without a shadow of a doubt. So I will just go there and see what y value I will hit, and I know that that y value will be 1.5 times 5, meaning it will be 5 into 1.5, which when you do it on the picture, you will see it will come to 7.5 meter, which is exactly the result you get from the equation. Now we get it from the picture of the equation as well, because y coordinate is 5 times x coordinate for every point on this line. The point that you will end up plotting when you actually do it, the point that you end up finding out will be 1.5 comma 7.5. So you don't have to sit and do the multiplication because every point on the equation on this line fits this equation. You just reach that point by holding time at 1.5. then you can rest assured that the y coordinate of that point will be 1.5 into 5. Just see what it is, you will get the answer 7.5, which is the same as what answer you got from the equation. So this picture gives us another way of computing different cases in the experiment, an alternative to computing it directly from the equation. Now we can also do the reverse application, right? So if you remember again, when we were making predictions using the equation, we saw the other case, right? Wherein you can also use the equation to get the value of x if you know the value of y, right? And we'll see that example here. In our situation, I have the equation y equal to 5x. Supposing I want to find out, again, a random stage in the experiment, what will be the time elapsed? So this time I don't know the time. I don't know x. What will be the time elapsed from the start when the car has reached the 12-meter mark from the start? So now what do I know? I know the y. I want to find out the x. So when y is 12 meter, what is x? And we know that we can get that also from the equation, right? So seeing how we do it from the equation, what we know is y is equal to 12 meter. The equation is y is equal to 5x. So if y is equal to 5x, then what is x? X is equal to y divided by 5. Just move the 5 to the other side, right? Multiplication on one side becomes division on the other. So x is equal to y by 5. Making the substitution, x is equal to 12 meter divided by 5 meter per second. Again, I'll get into the units a bit later on. The answer will come to 2.4 seconds. Please check my mental math. 2.4 seconds from the start, we got the value of x. Now, in case we don't want to do the actual division like this, we want the answer in an easier way, we can now do the same thing using the picture of the equation. How do we do that? Let's start at the origin. Now, the first movement we make cannot be along the x direction. It can't be along the x-axis because we don't know how much to move along the x-axis because we want to find out the time. But what do we know? We know how much to move along the distance axis, along the y-axis, because we know that we are looking for how much time has elapsed when the car has reached the 12-meter mark. So what do? Start at the origin. Now we will hold the time at 0 because we don't know how much time, right? Hold the time at 0, move only along the y-axis, along the distance axis, reach the 12-meter mark. Now that we reached here, we will lock it. Lock the distance at 12, don't move up and down anymore. Now start moving along the x-axis or parallel to the x-axis, same direction but little shifted. Move along the x-axis. As you move along the x-axis, the time value is changing, right? When do we stop? Go and hit the line. Why do you stop at the line? Again, because this point that is now on the line, because it is on the line, we know that for all the points on the line, the y coordinate of that point is equal to 5 times its x coordinate because it's on this line. Now, just like we rearrange the equation here, we can rearrange the equation here, right? Therefore, we can say the x coordinate of any point on this line is got by doing the y coordinate by 5. X coordinate of any point on this line is y coordinate divided by 5, which is great because now that means if I extend this line and hit this point which is on this straight line, I can be completely sure that the x coordinate of this point, which is basically this distance, right? The x coordinate of this point is what? How much you have to move along the x-axis to reach this point, right? Now, because this point is on this line, I can be 100% sure that this distance, right, which is the x coordinate of this point, because this point is on this line, this x coordinate, this distance will be the y coordinate of this point, which is 12 in this case, y coordinate divided by 5. No questions asked. And when I actually do it in the graph, you will see. Find this distance, bring it down and see how much it is on the x-axis. You will see it will be exactly 12 by 5. It will be the 2.4 second mark, which means this x coordinate of this point will be the 2.4 seconds that you got from the equation. Now you get it from the picture of this equation. And another way of saying that will be the point that you finally get will have the coordinates 2.4, 12. Now this can be extended to any later stage in the experiment as well, something that we looked earlier at as extrapolation. Extrapolation means, well, what if I want to know distance and time values for a much later stage? And in the earlier example, in the earlier lesson, we spoke of, what happens to y, that is, what is the distance traveled when x is equal to 500 seconds, right? And we did the same thing, put it in the equation, y is equal to 5x, x is 500, y is 2500, right? The same thing can be done with the picture as well, right? So just like we did it so far, start from the origin. You just have to extend the x-axis and y-axis to make the graph a little bigger so as to cover all those values. One way of doing that without having the graph becoming humongously huge is you can change the scale and shrink the graph, right? Without changing anything in terms of its actual shape, etc. Right? You can just change the scale. Then what you do, you just go to the 500 second mark, lock it there, and then chain the y. Go straight up and hit the line. Wherever you hit the line, that point's y coordinate will be 2500 meters. It will be 500 into 5 because every point fits the equation. You can do that, right? And the other reverse case also can be done for extrapolation, right? So we gave the earlier example as to what will be x, that is, what will be the time elapsed when the distance traveled is, say, 1000 meter, right? Again, you can get it from the equation. Now you know y, you put y as 1000 meter and therefore you get x as 1000 divided by the 5, y by 5 is equal to x, and you get the answer as 200 seconds, right? So we did that in the earlier lesson, so I'm not rewriting it here. The same thing can be done with this picture as well. Now you know y. So start from the origin, go to the 1000 meter mark on the y-axis, hold at the 1000 meter mark, then go straight. That means you're changing the x coordinate, go and hit this line. When you go and hit this line, that point that you hit, you can rest assured, because that point is on this line, that point's x coordinate will be the y coordinate divided by 5, because that point is on this line and all the points on this line fit this equation. And therefore, when you get that point's x coordinate, it will be 1000 divided by 5. You can do it and check. You will get on the x-axis a value 200 seconds, and therefore that point will be 200, 1000, right? Please correct me if I'm wrong, I'm getting old, right? So you can do this extrapolation as well from the picture. Now as we wind up, now that we've really, in a very organic way, figure out exactly what's happening here in the experiment, the equation of the experiment, the tables that come from the equation, and the picture that comes from the table, you realize that everything is just one story, right? We're just telling the same story in different ways so as to make our lives easier in terms of making calculations, computations, predictions, and getting a mathematical model of what's actually happening in real life. So now that we know why we do every step and what it's all about, now we can focus a little bit on the terminology and on the jargon, so to speak, right? This picture of this equation, which in this case is a straight line, the mathematical name we give it is a graph, right? So when we say graph, we are simply meaning the picture of this equation in our graphical plane, in this case in our Cartesian coordinate system. So in the Cartesian coordinate system, or in the Cartesian coordinate plane, in this case, how does this equation look? And therefore, how does this experiment look? In this case, it's a straight line. That is called the graph. So as far as we are concerned right now, the graph of an equation in this form, y equal to 5x, the graph of this equation is this straight line through the origin. Now, before we finally close up this long and at times unnecessarily detailed lesson, we're going to get into even more unnecessary detail, as is always the case with me. Now, everything is fine so far, but I have a couple of questions I want to leave you with. Now, I'll give you a disclaimer here. These two questions will be the first that I will be attending to in the next video, but this particular discussion right now is optional because it is just too detailed for where we are in the course right now. It's just for those of you who really have some extra free time on your hands. If you want to delve into it, I'm just leaving it out there, but it's completely optional. What we have done so far more than covers what we need going forward. But what I'm going to discuss right now will eventually, anyway, we'll come back to it, we'll circle back to it. I just want to leave it out here for those of you who want to delve deeper right away. But when the next lesson starts, you can completely skip this section. I'll also label it as optional. And why is that? I'll take you back to this diagram. I know that it seems like I've messed it up because I've drawn some weird snake-like pattern on the graph. Now you can use the word graph. I'll come to that snake-like pattern in just a bit. Two questions. Now, the first question is, when we plotted our first 6 points, we saw the way they lined up. It was really wonderfully neat. And when we did our Hansel and Gretel, we had no problem just joining them with a straight line because that's how they formed. That's how those are the kind of positions that they took. The question is, why? Why is it? What is it about this equation? What is it about these points that when I actually plotted them on the graph, they lined up so perfectly, they lined up so neatly, and we were able to join them with a smooth straight line? Why? Why did they not line up in some other shape? Maybe an S or a Z or a zebra or a line. Why didn't they line up like that? Why did they line up in such a way such that it was easy to draw a straight line through them? That's the first question. And then the second question. The second question is, okay, Hansel and Gretel, everything is fine, but can you really be dead sure? Can you really be sure that all the in-between stages in the experiment, say between these 2 points, that is between these 2 points in the graph, all the individual values of x and y, x and y, x and y, the individual stages, how can you be so sure, so precise and confident that those points will lie on this straight line? What if when I actually plot those points, taking each pair x, y, using this equation for all the points in the middle, what if when I actually plot them and I join them, what if I get a line like this? What if I get a snake like this? Which means it's like your worst nightmare. What if it's such a weird situation such that these specific points line up in a straight line, but all the other stages in between, they follow some sort of pattern like this when you actually do the plotting? What if it's like that? How can you be so confident that all those in-between stages will be along the straight line? What if they actually go like this, and only by some weird mathematical situation, only the points that we chose over here, because maybe they're all evenly spaced out, maybe because of that, these points were in the same straight line, but if you actually do the other points, when you plot them, what if you get a pattern like this? So the question is, how can you be 100% sure that when you plot all the other points, they will be on this straight line? Now, the explanation that we have gone through in this lesson covers it. It is pretty watertight. But if you want a deeper explanation, that is what I'll be addressing in the first part of the next lesson. It is way too deep for right now. We'll circle back to it anyway. So therefore, it's optional. But think about it. I'll see you soon. Namaskaram.